Good afternoon to all of you, the scientists present here, professors, and all the dear delegates. I am Swati Parashar, and I am going to present my research work known as TBHP assisted catalytic oxidation of styrene using copper shift base intercalated in layered double hydroxides. And thank you for giving me this opportunity to present me here. These are the contents. First one is the research highlight, then introduction, synthesis of catalyst, characterization of catalyst, catalytic activity, optimization of reaction condition, recycling, conclusions and references. Research highlights. The synthesis of my catalyst has been done under moderate conditions. Work has been done using non-poisonous transition metal, that is copper here, and highly stable heterogeneous catalyst under my reaction condition. The conversion of styrene is 66.19% under optimized conditions, and my catalyst has been recycled for the 10 times without any significant loss of catalytic activity. Introduction. The process of oxidation is an important procedure, and especially the oxidation of styrene plays an important role as it gives styrene oxide, benzaldehyde and benzoic acid as the product, where benzaldehyde can be used in the production of pharmaceuticals, agrochemicals, resin additives, perfumes, etc. While styrene oxide can be used as an epoxy resin, surface coating, perfumes, bulk chemicals, and if we talk about benzoic acid, then it can be used in its salt form in drug and food industries. In this field, shift bases are of great importance. Initially, they were used in their homogeneous form, but it suffers from non-reusability, contamination of product and separation of product, and hence concept of heterogenization comes in the community of this field. Now, for heterogenization of the copper shift base complexes, various supports has been used like alumina, clay, polymer, etc. Now, I am representing my work here, which is styrene oxidation by copper shift base complex intercalated in layered double hydroxide known as LDH SALBaCu. The catalytic activity of it has been used for the oxidation of styrene. This is the synthesis of catalyst which has been done in 3 steps. First step is the synthesis of support, that is LDH NH2C6H5COO, which is made by zinc nitrate and aluminum nitrate with alkaline solution of 4-amino-benzoic acid. Then when it is treated with salicylaldehyde in the methanolic solution for the 4 hours, then we get the product which is known as LDH SALBa, which is a ligand and it is in yellow colored. And when it is treated with copper acetate, then after 4 hours of refluxing, we get a brown colored solid material which is known as LDH SALBaCu, which is my heterogeneous catalyst. Now, these are the characterization of the catalyst in which metal content has been found out by ICP AES analysis, and it is found to be 6.53. The basal spacing is 15.66 in my support, while in my catalyst it is 20.36 angstrom. And if we talk about the elemental analysis, then these are the data of elemental analysis. If we talk about BT surface area, then the support is 10.15 meters square per gram of surface area, which increases to 18.84 in my catalyst. This is the XRD pattern. First one is of support and the second one is of copper. It is having spacing 15.36 angstrom along 003 of plane, and it increases to 20.34 angstrom in catalyst. This is the schematic diagram of LDH structure in which this copper complex is inserted into the layer of this layered material, that is layered double hydroxide, and the increasing of D spacing indicates that there is successful intercalation of this complex inside the layer of this support. This is the FTIR spectra which shows some peaks. The peaks in between the 310 to 3600 is due to the OH stretching peaks, and the one more important peak at 1615 is due to the imine peak C double bond N, which occurs in our ligand, and the peaks between 750 and 650 is due to the metal oxygen and metal nitrogen stretching. These are the same images of it which show the clearly flake-like structure. There is no much difference in between the support and the catalyst, which show that the properties of support remain intact in the catalyst also. These are the ADEX spectra which show clearly the presence of carbon, oxygen, zinc, aluminium, oxygen, nitrogen, and in catalyst it is showing copper also. These are the TGA curve. It shows the thermal stability of my catalyst, and there are some falls, two major falls. One fall in between 25 degrees centigrade to 250 degrees centigrade is due to the loss of absorbed water, and the second fall indicate the degradation of the brucite layer. This is the catalytic activity. The catalyst is LDH, SAL, BSCU. Styrene has been taken 5 millimole, and TBHP, which is oxidant in my case, has been taken as 10 millimole. So 1:2 molar ratio has been studied, and the reaction time was 5 hours while the temperature is 80 degrees centigrade. This is the scheme when styrene is treated with this catalyst in the presence of oxidant. Then we get styrene oxide, benzaldehyde, and benzoic acid. These are the optimization. Optimization has been done to calculate the some optimum conditions, and for it catalyst concentration, molar ratio, and temperature has been studied. First one is the effect of oxidant. When the ratio is increased from 1:1 to 1:2, the conversion increases, and when it goes to 1:3, then conversion decreases. Hence 1:2 has been taken as an optimum molar ratio. Now, the effect of catalyst concentration: when catalyst is 50 milligram and it increases to 75 milligram, then it gives conversion around 65%. And when it increases to 100 mg, then there is no much difference in between the conversion, and hence 75 mg has been taken as the optimum catalyst concentration. Now, the effect of temperature, it is clearly indicated that when in temperature increases from 70 to 80 degrees centigrade, then conversion increases. But there is no any marked change when we increase the temperature to 90 degrees centigrade. Hence, 80 degrees centigrade has been taken for optimum. Now, recycling of catalyst. This is the beauty of my catalyst. It can be recycled for the 10 times without significant loss. In first cycle, it has 66.19% conversion, which decreases to 56% in the 10th cycle, which is not so much of difference, and it is the beauty of heterogeneous catalyst also. Now, conclusions. LDH intercalated copper shift base complex has been synthesized by intercalation method. It is characterized by XRD, FTIR, ICP, AES, SEM, EREX, BET surface area, etc. Its catalytic performance has been studied for the oxidation of styrene, in which 66.19% conversion is obtained. The three products are obtained, which are styrene oxide, benzaldehyde, and benzoic acid, in which benzaldehyde is the major product. Now, the catalyst has been recycled for the 10 times, which proves it to be fantastic in the sense of stability, activity, and reusability. These are the references. Acknowledgement: I am thankful to Almighty God, my parents, and my supervisor, Dr. Savita Khare, and also the organizers of ISCA 2017 for giving me opportunity. Head School of Chemical Sciences, UGC DAE Consortium, SAF, IIT Mumbai, and STIC for providing analytical facilities. Thank you.